Okay, hi everyone. This is going to be a lesson on vector equations. If you've been watching the videos so far, you know that in the first two videos we talked a lot about linear systems and how to solve them. We talked about Gaussian elimination and Gauss-Jordan elimination and how you can solve systems using matrices, basically the augmented matrix of a system, and you do row reduction steps to try to get the matrix into a better form and read the solutions from there. What we do today in this video, it's going to seem a little different. We're going to be talking more about just matrices as objects themselves and things that we can do with matrices. It's going to seem for a little bit like we're moving on to a different topic, but then pretty soon we're going to come back to systems and see how this is all related. Okay, I guess that's the intro. Let's go ahead and get started. So the section is called vector equations, but before we can get to that, we have a couple of definitions. All of these first few videos are kind of heavy on definitions, just a lot of terminology, and it's because we're in chapter 1. And, chapter 1 of the course, we need to establish a lot of definitions so that we can work with these things later. So the first definition that I want to give is something that I think I may have mentioned in a kind of side note in the first video, and that is a definition for the word matrix. And we are just going to say that it is a rectangular array of numbers. And I'll tell you that the plural form, when you have more than one of these things, they are matrices. By the way, before we move on, I like to just kind of sometimes fill you in on some things that the book might not mention. We say that a matrix is a rectangular array of numbers. If you take further courses, like if you study linear algebra further, or if you're thinking about graduate school, you might see a different definition of matrix later on. It turns out that a matrix can actually be a rectangular array of anything. You could have other things inside there besides just numbers. But for our purposes, in this course, they will be numbers. And in particular, in this course, they will be real numbers. Now, we say a matrix is m by n, and we pronounce this that way. We say m by n, where m is the number of rows, the number of rows, and n is the number of columns. It seems like it's good to be able to refer to a matrix by the size since these things are kind of rectangular. So for example, do a quick little example here. This matrix is 2 by 3. It has 2 rows and 3 columns, so we always go with rows first. A column vector, I'm going to underline that. A column vector, or just vector, we might just sometimes call it a vector, is any n by 1 matrix. So if you put that together with what we said above, n by 1 would mean that there is 1 column. So a matrix that only has 1 column. And these are usually written as lowercase v with a little symbol above it to mean that lowercase v is a vector Or sometimes it can be a lowercase v with an arrow over it. That means the same thing for us. Or it can be a bold letter V. So when it's in a textbook, a lot of times they use the bold V, but I'm not going to do that much. You know, writing by hand, we typically use the first one. If you're typing it, you might use the bold one. All right, here's some examples. Examples of column vectors. They don't have to just be called V, by the way. You know, this could be other letters as well. So I'm going to give 3 examples. We're going to have U. U is the column vector 1, 2, 3. Here we go. That's an example of a vector. The next one, comma. All right, next one I'm going to call V, and this will be -1 and then 0. And the last one I'm going to call W. This one is going to have some decimals in it. Let's have 0.5, 0.75, 0.5, 0.25. Whatever. It's just a matrix with one column only. And you know in math we have certain conventions, like a lot of times variables are things like x, y, z. A lot of times constants are things like a, b, c. A lot of times functions are f, g, h. Well, u, v, and w are often used for vectors. And you can tell from these examples, they can be, you know, different sizes or different heights, and they can have repeated numbers in them. They can have zeros in them. Let's see, some more terminology. A vector of all zeros is called the zero vector. And it is sometimes written as 0 with the little vector symbol above it. Such as the zero vector equals vector with all zeros. And the size of it depends on context. You know, if I just use that symbol for the zero vector, you might say, how many rows does it have? You know, does it have 3 rows, 4 rows, 5 rows? And generally, it'll be clear from context. It'll be like we're in a problem where we're working with a bunch of vectors that have 3 numbers each, and then we say the zero vector, and we know that it has 3 zeros. Something like that to give us context. By the way, the numbers that are in a matrix or a vector, we can call them numbers. We can also use the word entries. We might call them entries. I know that in the previous video we talked about the leading entry of a row. The leading entry? Well, we can actually call any of these things entries. What else? Some other definitions or notation. Some of this you've probably seen before, but we'll just say that this is the set of all real numbers, right? The fancy looking R is the set of all real numbers. What we're also going to work with in this class is the fancy looking R raised to the lowercase n. And it is the set of all vectors with n entries. So if you want to talk about all vectors that have 3 entries, you could have R with a little 3 up there, where all the entries are understood to be real numbers. And one more little symbol that you've probably seen in another class is this symbol is the empty set. I guess I should say, you know, the empty set is not to be confused with 0 and not to be confused with the 0 vector. Those are 3 different things. 0, 0 vector, empty set. 3 different things, because this is an actual set. This is like an empty container. And by the way, most of what we do in this course is going to involve real numbers, but most of it applies more generally to complex numbers, in case you're wondering. Now, let's talk about equality. Equality of matrices. So 2 matrices, I'm going to say slash vectors. We know that a vector is just a matrix of a certain shape. 2 matrices or vectors are equal if they have the same entries in the same positions. So I'll show some examples of this. Example, if this vector equals this vector, then we must have a equals 3 and b equals 5. Both of those things would have to be true to say that these vectors are equal. They have an equal symbol in between them. All right, same entries in the same positions. Let me show you an example of 2 matrices that are not equal. So this matrix 1, 2, 3, 4, we would call that a 2 by 2 matrix. This is not equal to the matrix 1, 2, 3, 4 with some zeros underneath. Now, these 2 matrices, they have a lot of the same entries in a lot of the same positions, but not everything. I mean, the one on the right has some zeros that do not appear in the other one. And in fact, you know, this is a 2 by 2 matrix, and this is a 3 by 2 matrix, and it turns out that when you have matrices of different sizes, they can't be equal to each other. Because they can't have all the same things in all the same places if they're different sizes. Even if those things are zeros. The zeros matter. Give you another example of 2 matrices that are not equal. How about the matrix 2, 4, 6, 3, 7, 12 is not equal to the matrix 1, 2, 3, 3, 7, 12. So why am I pointing this out? I mean, you look at them and you say they have different numbers. Different numbers, right? So different entries. But the reason why I wanted to mention this is that what's the difference between these? It looks like I took row 1 and multiplied row 1 by 1/2. So I did a row reduction step to get from one matrix to the other. I multiplied row 1 by 1/2. That is a valid row reduction step. But I'm going to say that these matrices are not equal, even though their corresponding linear systems have the same solution. Okay? So they are row equivalent because we performed a row operation. But being row equivalent is not the same as being equal. It's not the same as an equal sign. And you know that in the first two videos that you've already watched, when we were solving systems, we were doing row operations and row reduction. We didn't put equal signs between those matrices. We usually put arrows pointing to the right with some little indication of what step we did. And that's okay to put arrows. Don't put equal signs between matrices when you're doing row reduction, because they're not equal. All right, so that's a little bit about what it means for two matrices to be equal to each other or not equal to each other. Let's talk about some things that we can do with matrices. So we're going to talk about sums and differences. Sums and differences. So all that we need to do is add or subtract corresponding entries. If we want to add two matrices or subtract two matrices, whether they are vectors or larger matrices, I'll show you some examples. This matrix plus this matrix. All we do is add the corresponding entries. So this is a 2 by 2 plus a 2 by 2. The result is also going to be 2 by 2, and the entry in the upper left gets added to the entry in the upper left. 1 plus 6 is 7. The entry in the upper right gets added to the entry in the upper right. 2 plus 3 is 5, and so on. So we can add the corresponding entries. That's how you add two matrices. Now, this only works if the matrices are the same size. Otherwise, it's undefined. Like if you try to add two matrices of different sizes, that's just undefined. I don't think we'll really find ourselves trying to do that. Let's do a subtraction, just to show that it works the same way. And subtraction should work the same way, because when you subtract something, you're just adding a negative number. All right, so we can subtract corresponding entries. I think over here I've got 1 minus 2, negative 1. 2 minus 1 is 1. 3 minus 1 is 2, and 4 minus 2 is 2. So adding or subtracting matrices like this is fairly easy. There's some other things we can do as well. We can do what is called a scalar multiple of a matrix. So in this case, we scale all entries up or down. I'm going to show you two examples of this. This is basically going to be when we have a number times a matrix. So instead of, a number times a number, or a matrix plus a matrix, this is number 3 times this matrix. So if we say 3 times this matrix, what we're going to do is say, let's do 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12. We basically scaled up every entry of the matrix by a factor of 3. And the result is the new matrix has all the entries being 3 times bigger instead of 1, 2, 3, 4, 3, 6, 9, 12. Here's another one. So when would we scale down? We would scale down if it's something like this. So let's say 1/2 times this matrix, and this matrix happens to be a column vector. So if we wanted to scale it by a factor of 1/2, we just do 1/2 times each entry. 1/2 times -4 is -2, and 1/2 times 5 could be written as a decimal or a fraction. I chose to write it as a decimal. Each entry is now half of the original vector. On the topic of doing scalar multiples, we might refer to this as scalar multiplication. Got a little bit of terminology I'll just say over here. If we're given a vector, and let's try to be general now for this little side note. Let's say the vector is u, and let's say it consists of two entries, u1 and u2, which are just real numbers, and a number lowercase c. We have cu equals, all right, so this looks like I'm trying to do a number times a vector. And that's what we just did to the left, right? But this is just more general because we're using letters instead of specific numbers. But this would be c times this vector, and it equals cu1 times cu2. And the little piece of terminology that I wanted to mention is we call c a scalar. In this context, the number c is a scalar. It's a real number. It's probably a constant in most cases. But yeah, that's when you say scalar multiple, c is a scalar. So in this course, the objects that we tend to deal with the most are things like scalars, vectors, matrices, equations, so we'll throw the word scalar around sometimes when we're just talking about a real number in this context. Let's move the page up a little bit. I'm going to have a short little question for you to try. Example, let's say we're given c equals 5, d equals 2/3, the vector u equals this vector, and the vector v equals this vector, 12, -30. I'm going to ask you to try this. I want you to find cu plus dv and simplify your answer. So why don't you take a minute and try this? I would recommend that you pause the video and try this for a moment, and then I'll talk about it. All right, so this is one type of problem you could see from this section. We're doing more things in this course besides just solving systems. All right, what have we got here? So cu plus dv would look like 5 times this vector plus 2/3 times this vector. And I said that we should try to simplify it, So what do we get here? Let's do the actual scalar multiplication. So 5 times the first vector gives us -5 and 10. And then 2/3 times the second vector, 2/3 of 12 is 8. 2/3 of -30 is -20. And there's one more thing we could do to simplify this. We did the scalar multiples, but now we have a vector plus a vector. Let's just add the corresponding entries. -5 plus 8 is going to give us 3. 10 plus -20 is going to give us -10. And that is a nice simplified answer. All right, so that's just a little vector arithmetic we're doing. let's talk about vectors in R2. You know how I said that if you have R with the little n up there, we're talking about vectors with that many entries. So this is going to be vectors with 2 entries. I'm going to say that there is a one-to-one relationship between vectors xy in R2 and points x comma y in the Cartesian plane. By the way, what is the Cartesian plane? Cartesian plane is just another name for the xy plane. It's where we do most of our graphing if it's two-dimensional. So the one-to-one relationship is just saying that we can think of these objects as column vectors. You know, it's a column of 2 numbers. Or we could just think of it as corresponding to a point. You know, the vector. Here, let's write some of this instead of me just saying it out loud. A vector such as, I was about to say something like this, so let's just write it. A vector such as 2, 1 is often drawn with an arrow from the origin to the point 2, 1 to indicate direction. Arrows to indicate direction. So I'll draw 2 little pictures here. Drawing the Cartesian plane. I'm going to label the x-axis, y-axis. Let's just set up both of them. All right, so the origin is at 0, 0. If I draw an arrow from the origin to the point 2, 1, it would look something like this. And we call this the vector 2, 1. On the other hand, traditionally in math courses that we've had before this, we're used to thinking just in terms of points, and we would just have a point there. There wouldn't be an arrow, and we would call that the point 2, 1. So there's pretty clearly like a relationship where we could translate back and forth between one and the other. You know, we could say the vector 2, 1 or the point 2, 1. They're really kind of just different perspectives. And we can work with one or the other depending on which one is more convenient. Those of you who might take Calculus 3 or might be taking Calculus 3 now, Calculus 3 works with vectors a lot, especially at the beginning of the semester. A lot of other courses just work with points. Depends on what is convenient. This leads us to what is known as the parallelogram rule. So if the vector u, you know these are vectors as soon as I write the symbol above them, okay? If these 2 vectors in R2, so you know they have 2 entries, are represented as points in the plane, then u plus v corresponds to the fourth vertex of the parallelogram whose other vertices are u, the zero vector, and v. I'll draw a picture of this. This is definitely a very visual idea. We're talking about parallelograms, so let's try to draw a picture of one. You notice the zero vector showed up in this sentence. The zero vector would just correspond to the origin, wouldn't it? 0, 0. All right, example. Let's draw a picture of this parallelogram rule and see how this parallelogram shows up. So let's say what kind of scale do we need here? Let's go 1, 2, 3. One, 2, 3, 4, 5. That should be plenty. Okay, let's say I have a vector u, and the vector u goes like this. And I'm going to label it right here with a vector symbol above it. There's the vector u. Let's say I also have a vector v. I'm also going to show v as an arrow originating from the origin, going off into some direction for some length. Let's say this is the vector v. So the parallelogram rule says something about what happens when you add u plus v. So first of all, I'm going to do this off to the side as vectors. I'm going to say u plus v equals, I would say that the vector u appears to be the vector 2, 1. And the vector v appears to be the vector 1, -1, because that's where it appears in the Cartesian plane. Here's -1 down here. Right? We're just thinking of what points these arrows are pointing to. 2, 1, and 1, -1. When you add these, you just add the corresponding entries. So 2 plus 1 is 3, 1 plus -1 is 0, so I get 3, 0, which itself is also a vector. Let's try drawing this vector. I'm going to use blue for this. This vector 3, 0, again, I'm going to draw it as an arrow starting from the origin, but it's going to go to the point 3, 0. So it's going to go, well, it's kind of on the x-axis, but here it is. That's where it went. So what is special about that point? Well, the parallelogram rule says that the sum that we got, 3, 0, this should correspond to the fourth vertex of the parallelogram whose other vertices are u, 0, 0 vector, and v. So we do, in fact, get a nice little parallelogram if we were to connect these. And that is what the parallelogram rule is saying. It's not just a coincidence that this took us to 3, 0. It had to take us to 3, 0 to get us a parallelogram. So that's kind of a little connection to geometry even. You know, occasionally we'll see connections to other areas of math here. So I want to say that let's note vectors in Rn such as the vector 2, 1 are sometimes written as the point 2, 1. And this is due to the one-to-one relationship between vectors and points. We might find it more convenient to work with them in one way or another, depending on context. All right, so just be aware of that. All right, so we have been talking about Rn, and we have a lot more to say about Rn, and we're going to start with some properties. Properties of Rn. This seems like an important topic because this is the set of all column vectors with n entries, which we're now saying can also be thought of as the set of all points with n coordinates. So we're going to have a list of properties for all u, v, and w in Rn, and all scalars, we know what that means, c and d. Ready for a list of properties? Let's go. Number 1, u plus v is the same as v plus u. Simple enough. That's called the commutative property, but I'm just going to be listing these. I don't think I'm going to tell you like the names of all the properties. But we could actually sort of prove this by using what we've said so far about how you just add corresponding entries, and we know that ordinary addition of real numbers has this kind of property. So that kind of follows from that. Another property is with parentheses, the vector u plus v plus w with those parentheses is equal to this. So on the left-hand side, if you added all those vectors together, you'd get a vector. On the right-hand side, if you add them all up, you'd get a vector. And we're saying that they are the same. So the parentheses tell us which thing to do first. The property is telling us it doesn't matter whether you add u plus v first or add v plus w first. Either way, you're going to get the same result. Some of these might seem like common sense. How about this? The general vector u plus the 0 vector equals I'm going to say this equals two things. First of all, it equals this, and that they both equal this. I probably could have left out that middle part. But yes, when you add the 0 vector to u, you just get u. It doesn't change the vector. And in this case, you know, the size of the 0 vector would be the 0 vector in Rn. Property 4 is that the vector u plus negative u equals negative u plus u, and that either way, it adds up to the 0 vector. We have properties like this for real numbers, like, you know, you could say 5 plus negative 5 is 0, right? But we're now saying these kinds of properties hold for vectors in Rn. I should tell you for this property, off to the side, I'm just going to say where negative u denotes negative 1 times u. Like if there was any ambiguity here, if there was any question about what does negative of a vector mean, because that might be the first time we've really used it that way, negative of a vector just means negative 1 times the vector. Property 5, this is where we're going to get some of those scalars involved. C times u plus v equals cu plus cv. So that's kind of like a distributive property. There's going to be a couple of different properties that could be described as distributive. We're kind of distributing the C across these parentheses. And it just says that distributing a scalar across parentheses kind of works the way that you would expect it to. The next property is, what if we have two scalars being added together and then a vector? And maybe you could think to yourself before we finish this, you could think, how would you expect this to work? Like, how would you expect those parentheses to act? Well, it does work that you get CU plus DU. You can distribute the C times the vector plus the D times the vector. I think on this list we have two more to go. Property 7. This is going to have scalar C times scalar D times U. And this property says that that is equal to CD times U. Instead of doing D times U, like the parentheses are suggesting that we do D times U first and then multiply by C, this property is saying that it's okay to just multiply the two scalars, CD. Multiply them together and get one scalar out of it, and then multiply it by U. And one more for now is property 8. Property 8 says 1 times U is U. Again, like I said, it might seem like some of these might seem like common sense. This is basically saying, you know, we talked about doing a scalar multiple. And in fact, I think when we talked about the scalar multiple, I said something about how you scale all entries up or down. Maybe I should have said you scale up or down or equal, right? Or equal, because in this case, we're not scaling it upward, we're not scaling it downward. It's just 1 times each entry. Now, some of these might seem like common sense, but that's not really good enough for us in math. We would like to prove things in math. So I think what I'll do is I'm going to prove one of these for now. Some of these you could prove on your own for practice, but I think it would be nice for me to show you one just to get the general idea of how we work with these. So let's prove property 1. Property 1, let's write it again. Property 1 says that U plus V equals V plus U. We can't just say it's true because it looks true. So, proof. Let's establish what these vectors U and V consist of. Now, we could write them as column vectors, but I think sometimes in a proof, it's going to be more convenient to write them as coordinates. Remember above, we said that we could write it either way. So I'm going to say, let's let U equal U1, U2, up to UN. And let's let V equal V1, V2, up to Vn. And let's let them be any vectors in Rn. Okay, good. Good way to start. Then, let's see what happens when we add them together. We want to show left-hand side equals right-hand side. Let's start with the left-hand side. U plus V is equal to... You know, earlier we said that when you add two vectors, you add the corresponding entries. So the first entry that we get here should be U1 plus V1. because that would be us adding the corresponding entries. So we get u1 plus v1, u2 plus v2, dot, 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 all the way up to un plus vn. Let's keep going with this. This equals, wouldn't it be okay for each of these entries, wouldn't it be okay to swap around the order of these two things? Like u1 plus v1. Wouldn't it be okay to say v1 plus u1? And for the next one, I could call it v2 plus u2. And for the next one, for the final one, vn plus un. I can say that because we know that that works when you add two real numbers together. These are real numbers, and when I add two real numbers together, the order doesn't matter. Well, in a proof, if we want to be explaining why this works, we should say something like, by commutativity of addition in the set of real numbers. All right, addition is commutative in the reals. And finally, we can say, what does this equal? We have v1 plus u1, v2 plus u2, vn, we could actually split this up. Instead of taking two vectors and combining them into one, we could split this up and say that what we actually have here is v plus u. And that's exactly what we wanted. So all we really did in this proof, I'm going to put a little symbol here to say that's the end of the proof. We'll shade it in square. All we really did was establish that u and v are general vectors in Rn. We started adding them together. The real key to this was using a property from the real numbers. And that's why this winds up being true. And you could prove some of these other ones in a similar way. Like I'm looking at property 2 right now and thinking property 2 is called the associative property, and associative property also works for addition of real numbers. So similar idea, could prove some of these other properties. Let's see. We've established a bunch of those properties. They basically say that vectors and scalars, they kind of work maybe the way that we would expect them to. I don't think there was anything in that list of properties that was really shocking. Leads us to a definition. Okay, definition. Let's say we are given vectors. We need a bunch of vectors now. So we're going to be general. We don't know how many of them there are. I'm going to say we have v1, v2, up to vp in Rn. And we need a bunch of scalars for this definition. So we're going to say C1, C2, up to CP. We could say that that's in R, but we don't have to necessarily say that. We said scalars. That's good enough. I haven't gotten to the definition yet. We're just setting up a bunch of stuff. But let me just mention that this is the first time I've had vectors with little numbers at the bottom, little subscripts. V1 in this context is a vector with n entries. V2 has n entries. VP has n entries, right? So each of these is a big object. The vector y defined by y equals C1 V1 plus C2 V2 plus dot 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 all the way up to CP VP is called a linear combination. Let's underline that. A linear combination of V1, V2, up to VP. So Y is a single vector that you get by combining a bunch of other vectors in this way. You do this scalar multiple of, C1, V1, whatever that results in, C2, V2, whatever that results in. You do all of these, and then you add them all up. Ultimately, the result that you get is just a vector that lives in Rn, but it's a linear combination of the vectors that it came from. We say C1, C2, up to CP are called. You might think that I'm about to say coefficients. They kind of feel like they're coefficients, but it's a different word. We call them the weights. Now, it makes sense that we might call them the weights if you think about what it looks like to do like a weighted average. I'm not even talking about vectors right now, but just in algebra. Like if you do a weighted average, you have things that you could call weights. So anyway, this is going to be an important definition for us. I'm going to show you a little example. And in fact, this is an example from earlier. Sometimes I like to show you something without telling you. Like, basically, we've done a linear combination already, but I didn't use that phrase. Sometimes I like to show you something, and then I can come back and say, hey, you know that thing we did? Turns out that was a linear combination. So an example from earlier is we had this 3, -10. That was an answer that we got from a problem. And it is a linear combination of this vector and this vector, if those looked familiar to you from a problem we did, because we found that 5 times this plus 2/3 times this equals this. So in a way, it's a vector that is kind of a combination of other vectors and scalars. And it might not really be clear right now, like, why are linear combinations important? Like I said that this is an important definition for this course. We're gradually we're going to see why it's important. It's kind of telling us how vectors are related to each other. How about this? I've got a little problem I'd like you to try. On this topic, I'd like you to try to find C1 and C2 so that C1 times this vector plus C2 times this vector equals this vector. So take a couple of minutes, maybe pause the video, see if you can figure that out. So what I've really asked you to find here, it looks like I'm really asking you to find the weights. C1 and C2 would be the weights, and all the vectors are given. This seems to be suggesting that 7, 5 is a linear combination of these other two vectors if we can find the appropriate weights. So let's work on this solution. Well, we could take the way this is written, we could say C1 times 2, 2. We know what that means. That means C1 times 2, C1 times 2, right? Like a scalar multiple means you multiply C1 times each entry. And the same thing with this over here. C2 times 1, C2 times 3. And we want this to equal 7, 5. I'm going to simplify my left-hand side here. We could add these two vectors, by the way, and we could, instead of writing C1 times 2, we could write 2C1. So how about this? I have a vector that has 2C1 plus C2, and I have a vector that has 2C1 plus 3C2, and that vector allegedly equals this vector. And this thing on the left is just a column vector with two entries. It looks like I drew like a wide rectangle or something, but it's just a column. It just happens to look wide. It's the same size as this column vector. There's a top entry and a bottom entry only. Hey, didn't we say earlier that when we talked about matrix equality, if two matrices are equal to each other, that's only true if they have the same entries in the same positions? So we have to have 2C1 plus C2 has to equal 7, and 2C1 plus 3C2 has to equal 5. Just as entries, like in order for the top entry to equal the top entry, 2C1 plus C2 has to equal 7. And for the bottom entry to equal the bottom entry, 2C1 plus 3C2 has to equal 5. It turns out that we got two little equations, and we're saying both of these equations have to be true. I could put a little bracket next to them and think of this as a system. In fact, the unknowns, C1 and C2, that's exactly what we are looking for, and that's exactly what we would find if we solve this system. So let's try to solve this system. Let's write it as an augmented matrix. Maybe in the previous videos, we're used to the unknowns being like x1 and x2. This time it's C1 and C2, but it's still the same idea. So we're going to solve this system. It'll tell us what C1 and C2 are. And I want to remind you that I think at the end of the last video, I said something as a little side note. I said something about how almost every problem in linear algebra can be turned into solving a system of some sort. And it looks like that's exactly what's happening here. This didn't look like a solve the system type of problem, but we turned it into one. So I'm going to do Gaussian elimination. I am going to add negative R1 to R2. It's up to me if I want to do like the full Gauss-Jordan elimination to get reduced row echelon form, or just regular Gaussian elimination to get like triangular form and do back substitution. I decided to keep going, and I'm going to multiply R2 by 1/2. I tend to do that whenever I see like a 2 and a negative 2. I say, that would be simpler if we just multiply it by 1/2. Next, I'm going to add negative R2 to R1. And that gets me 2, 0, 8, 0, 1, negative 1. That's almost reduced row echelon form, except we have a 2, and the leading entries are supposed to be 1s. So now I'm going to do 1/2 times R1. To turn that 2 into a 1, it also happens to turn the 8 into a 4. So the solution that we wind up getting, the first row is telling me that C1 is 4. Second row is telling me that C2 is negative 1. And these are the weights that we were looking for. And those are the only answers. Those are the only answers to this problem. You could go back to the original problem. You could put in 4 and negative 1 and verify that it works. It wouldn't take very long to do that. I'm not gonna do the whole thing, but I'm just gonna show you, like, here's the problem. Can we see that, like, putting 4 and negative 1 in here would work? Like, if I put a 4 here and a negative 1 here, this would be like 8, 8, right? You figure it all out, you'd get your 7, 5. It would work out. All right, so we will talk more about linear combinations in a few minutes, in fact, but I want to tell you a little bit of notation here. The matrix. I'm going to do a 3 by 3 matrix for this example. May be written sometimes, depending on what we're going to do with it, sometimes it might be convenient to write it as V1, V2, V3, where V1 is the first column, V2 is the second column, and V3 is the third column. If we do that, we're writing the matrix just kind of as a collection of 3 columns. And maybe sometimes that could be useful to think of that way. Instead of writing it as a grid of 9 numbers, we think of it more as a collection of 3 columns, and this is what those columns happen to be. So I think we're going to use that in this next fact. So fact: a vector equation x1 a1 plus x2 a2 plus dot 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 up to xn an equals vector b has the same solution set as the linear system whose augmented matrix is, this is where I'm going to write a matrix as just a collection of columns. A1, A2, dot, dot, dot. We don't know how many there are, up to AN. And finally, the right-hand side, B. There's a little bit more to this fact that I'm going to write on the next page. But let's look at what we've said so far here. So I said a vector equation, and it is an equation because it has an equal sign, and the left-hand side looks to be a bunch of vectors being scaled and added together. The right-hand side is just b, which is a vector. So this vector equation, we're saying, has the same solution set as just the linear system with this augmented matrix. So the vector equation has a solution, and therefore B is a linear combination of A1 through AN only if the linear system has a solution. Let's think about this for a minute before we just move on to the next thing. So in this fact, it seems to be saying that there is a relationship between whether or not something is a linear combination of something else and whether or not a certain system has a solution. Well, I have to move things just a little bit to make a point here. That completely makes sense with what we just did above. I gave you a problem where I asked you to find the weights. I asked you to, I asked you to do this. I was basically asking you to find the weights to make 7, 5 a linear combination of these two vectors. And it could turn out that, well, maybe there are no weights that make this work. Maybe 7, 5 is not a linear combination of these two. It depends on whether or not we found C1 and C2. We turned the problem into the problem of solving a system. The system did have solutions. Therefore, that vector 7, 5 is a linear combination of the other two. Now let's look at the fact again. A vector equation, kind of like the one we started with. This is like saying B is a linear combination of the A's. If this augmented matrix system has a solution. And we know that not every system has a solution. So that means not every linear combination that you try to set up is going to work. Not every vector is a linear combination of any combination. So here, let me show you an example. So some things are linear combinations of other things, some things are not. How about this? X1, and right now the x's are kind of acting as the weights. It's okay that they're called x. X1 times that vector plus x2 times this vector equals this vector. Let's say I set this up. This seems to be suggesting that 3, 3 is a linear combination of 1, 0 and 2, 0 if we can find the appropriate weights, x1 and x2, that make this whole thing true. However, I don't think there are any weights, x1 and x2, that are going to make this work. The reason why I don't think it's going to work is because of this 0 and this 0. I don't think there's any weights that when I put this all together are going to give me a 3 down here. Something times 0 plus something times 0 equals 3. That doesn't seem like it's going to work. So this actually has solution set, empty set, because let's just be clear about this. When you set up the augmented matrix of the system, that's what it would look like. And this has solution set this. So going with that fact up above, the vector 3, 3 is not a linear combination of 1, 0 and 2, 0. Okay, now 3, 3 might be a linear combination of some other vectors. It probably is, but not these two vectors. So sometimes things are linear combinations of what you want, and sometimes they're not. And it kind of comes down to solving a system. So I think this section has, I think linear combination was an important definition that we're going to be using quite a bit this semester. And we also have another important definition coming up now. Because we're still near the beginning of the course, we're trying to establish lots of terminology definitions, the big ideas that we're going to be able to do lots of things with. All right, definition. Let V1, V2, ... up to VP. Let these be elements of Rn. This is my first time in this course using this symbol, but I think you've probably seen this before in a previous course like theory of proof. We're just saying that these are elements of Rn. So these are all vectors with n entries each. The set of all linear combinations of V1, V2 up to VP is denoted by span brackets V1, V2 to VP, and is called the subset of Rn spanned by or generated by V1, V2 up to VP. Going to underline or maybe put a box around this. I don't know. Let's just underline it. Span. So let's think about this. Can you imagine the set of all linear combinations of something? So maybe we have, I don't know, 10 vectors. We didn't even say what n is. We're being pretty general here. Maybe n is 3. Let's say you have 10 vectors that have 3 entries each. And then you take the set of all linear combinations of them. That's going to be a very big set, right? Because there's so many different combinations that you could make. You could add the 10 vectors together with various weights in front of them. So really, this is a very large set. It might actually be so large that it might be actually equal to Rn. It might give you like every possible vector of that size, or it might not. It's a subset of Rn. We know that for sure. In some cases, it could be all of Rn. All right. Or you could also say, well, what if we had a smaller example? What if you just had like two little vectors in R2? Maybe you take like these two vectors, 1, 0, 2, 0, and you imagine like the span of the two of them. That's going to include some vectors from R2, but it's not going to include this one. It's not going to include every vector. All right, let's say a little more about this. Okay, so that is span of V1 through Vp is equal to the set of all vectors that can be written in the form, I want to say all linear combinations. So another way of saying that is all vectors that can be written in this form. C1 V1 plus C2 V2 up to CP VP. For some scalars, C1, C2 up to CP. If those scalars exist, then there you go. So we're almost done, but I want to say just a little bit more about this concept of span. Let's say what kind of question you might see about this. How about if I ask you, is a given vector in the span of some other vectors? I think this seems like a yes or no question. If I give you a vector, is it in the subset of Rn spanned by these? Is it in span of these things? This means, is U a linear combination of V1 through Vp? That's also a yes or no question. So, does there exist a collection of scalars C1, C2 up to CP called weights, so that C1 V1 plus C2 V2 all the way up to CP VP equals the vector in question, U. This is still a yes or no question, right? This is the same as solving a system, right? Does this system, sorry, I need to keep moving up my page. does this system have a solution? It is a yes or no question. Let's look at this whole thing for a minute. So if I give you a particular, like maybe I give you the vector u, and I give you the v's, and I ask this as a question, is this vector in the span of these vectors? It's really me asking you, is u a linear combination of those vectors? Which it might be or it might not. It depends on whether or not weights exist so that this is true. Because if this works, if this is true, then you've got a linear combination with all the weights. And in order to find out if those weights exist, the best way to find out is by setting up this system and finding out if this system has a solution. Because if this system has a solution, that solution will be the weights. So examples from earlier. So we're really just kind of summarizing, because these were two examples that we already talked about. But number one, we showed, we might not have been using this terminology, but we showed that the vector 7, 5 is in the span of 2, 2, and 1, 3. Okay, we showed this because we found the weights C1 and C2. Let's see, what were they? I think they were 4 and -1. It was that problem. Another example, we said, we didn't really, I'm using the word said because we didn't really spend a lot of time on this, but we said that 3, 3 is not in the span of 1, 0 and 2, 0. Because we said that such a linear combination does not exist. Which you can tell by trying to solve the appropriate system and finding that the system has no solutions. It's an inconsistent system. But I also think that we can kind of tell because of these zeros here. I feel like we'd be trying to set up weights to get something times 0 plus something times 0 to equal 3, and I don't think that's ever going to work. So notice that this is the, first example 1, that symbol means this is an element of this set. Down here, there's a slash through it because this is not an element of this set. So when you say span of something, you're talking about a set of lots of vectors. And something is either in it or not in it. So that is one type of question you could see from this section. Is just here's a vector, like something like this with a yes or no, yes or no question. Is this an element of this, true or false? Maybe show your work, explain why. All right, so I think we're going to wrap things up here. Okay, so it seems like we are really going full steam ahead with the course, aren't we? Because we're really covering a lot in these first few videos. So if you feel overwhelmed, I would encourage you, Try to take notes while you're watching these. Maybe try to watch them twice if you need to, especially the parts that seem tricky. Also, reference the recommended textbook, because I am following a textbook and you might find some help there. Sometimes it helps to get my perspective and get the author's perspective, put the two together, and everything will click. You should also be trying to work on practice problems. You might have to struggle with them a little bit at first, but that's part of what math is all about. You struggle with some problems, but then things will click. You get that light bulb to pop up and everything makes sense. It's not easy, but I know everyone here can do this. And yeah, I'll say that that's it for now. That was vector equations. The first two sections were about solving systems. This section started out just being about matrices, but then we did wind up solving some systems towards the end. In this section, in your notes, if you wanted to highlight anything, I would say that the definition of linear combination is going to be important, and the definition of span is going to be important. I'm not saying that the rest of it isn't important, but those are two of the big ideas. All right, so that's it. And take care, everyone, and I will see you soon.